The Secrets of Let's Science is brought to you by the StarQuest Production Network and is made possible by our many generous patrons. If you'd like to support the podcast, please visit GiveStarQuest.com.
3, 2, 1.
We live in a universe of scientific wonders.
Every day, scientists are inching towards breakthroughs which can change our lives.
We're playing our small part in sharing these wonders with you.
That's why today is a fine day for science.
So let's science.
So Caroline, every so often I have a sweet tooth, and I like some a sugary snack. But I can't always find the sugar in the kitchen. And there are other places where I could find sugar, though. So, Caroline, where else can I find sugar if I need some?
Well, you're in luck. You're in luck. I have a very, very sweet topic for you today. Okay. Yes. And we're going to direct ourselves to the sky. We're going to look up in space. Okay. So, we've all seen the amazing pictures of gas clouds taken in space by various amazing telescopes to, let us see the things that we would never otherwise be able to see. Okay. And let's think of the gas clouds. So we know through decades of research that those dust clouds are like, little laboratories. They perform complex experiments. They create molecules of all shapes and sizes and function. And, of course, there's the birth of stars, which is super phenomenal. Now, but today I want to talk about something a little bit smaller than a star, quite small. It's the little molecule of sugar. So we've had the first confirmation of the detection of an actual sugar molecule drifting in the deep space between the stars. And this was described in a paper published in Nature Astronomy by an international team of researchers titled Detection of a Chiral 4-Carbon Sugar in Interstellar Space. Now, what does that mean? We'll go into it. So
I look at the sky sometimes at night and just think, is there a cupcake out there with my name on it?
There
or
might
a donut?
be. There might be. Yeah.
Oh, you're giving me hope with this topic.
Now, we talk about, the beginning of life. So when astrobiologists look for signs of life, they look for ingredients such as amino acids, lipids, and sugars. So amino acids are the bases of proteins, lipids are fats, and of course we know sugars are, we use it in our body. It's the backbone of DNA, etc. Now, sugar are the fuels of metabolism. They, like I mentioned, they form the structural backbones of RNA and DNA. And while we've previously detected sugar-like molecules or found complex sugars locked inside meteorites and samples, remember the asteroid Bennu that we've spoken about before? Well, we've never actually spotted a true sugar floating out there in space. Now, the one that they're talking about is a sugar called erythrulose. So on Earth, it's a natural sugar and it's actually found in raspberries, okay? It doesn't mean there's raspberries floating out at space, but, we haven't spotted that yet, so we don't know. We don't know.
Yeah. Okay. There's a raspberry out there somewhere.
There could be. Yeah. There could be.
Yeah.
So to find this interstellar sugar, researchers looked deep into the Milky Way galaxy, our own beautiful galaxy, pointed the instruments towards the massive target located roughly 26,000 light years away from Earth. And this target is actually a giant molecular cloud known to astronomers as G plus 0.693-0.027. I don't know why they haven't given it a different name. Okay.
That's memorable. Just like trying to remember a phone number, right? That's a very memorable. Yeah. I can remember that. Yeah, sure.
100%.
Yeah.
Now, this cloud is situated in the central molecular zone, which is a chaotic dense ring of gas orbiting just a few hundred light years away from Sagittarius A star, which is our galaxy's supermassive black hole, which we've also spoken about before.
Oh, wow.
So to understand what this cloud is, we have to picture the structure of space itself. So interstellar space is filled with clouds of gas and dust, And some of these are diffuse and hot, but others, like our one that we're speaking about today, G plus 0.693-0.027, are what astronomers call dark molecular clouds. And these regions are very, very cold, which is, they say, about minus 260 degrees Celsius.
It's like an
Freezing.
average morning in Melbourne. Yeah, gotcha. Right. yeah.
Exactly. Exactly. They're also very dense compared to surrounding space, and they're packed primarily with molecular hydrogen and tiny microscopic dust grains composed of silicates and carbon. And because these clouds are so dense, they block out the external radiation from nearby stars, and this acts kind of like a shield. Now, why the shield is important is because in open space, we know stars are constantly blasting out intense high energy, radiation such as UV light and X-rays, etc. And this is a kind of very destructive environment. Now, when high energy UV photons hit a molecule, it triggers a process called photodissociation. So what happens is the light is so intense that it overpowers the chemical bonds holding the molecule together, which snaps them instantly and tears the molecules apart into the basic atoms that it was made from. So while simple molecules like molecular hydrogen are tough enough to survive the cosmic onslaught, complex organic molecules such as erythrulose that was discovered have delicate, intricate molecular frameworks. So if they were exposed to the unshielded radiation, they would be destroyed. So this is where the dark molecular cloud acts as like a sunblock. So the microscopic dust grains inside the dust cloud absorb and scatter the harsh, high-energy UV light onto the cloud's outer edges. Then visible and UV light is completely blocked outside the cloud, leaving a freezing pitch black sanctuary inside the cloud's core. And this is where atoms can settle onto dust grains, bond, and build complex structures like the sugars without the constant threat of being ripped apart by nearby stars. So the unique location of G plus 0.693-0.027 near the galactic center introduces another crucial variable. Yes.
Space Wendy's can I help you. Sorry.
So inside is intense turbulence. Now, driven by the immense gravitational tug of the core and shockwaves from supernova explosions, gas within this cloud is constantly colliding. This turbulence drives a fascinating kind of chemistry. In the cold depths of the cloud, the molecules form on the icy outer jackets of dust grains, and they're stuck in place like frost on a window pane. However, when a low-velocity shockwave tears through the cloud, it collides with the dust grains, and this actually causes a process called sputtering, where the mechanical energy of the shock gently warms and strips the ice layer, violently ejecting intact complex organic molecules off the dust grains and into the surrounding gas phase. So once suspended as a free-floating gas, the molecules become prime targets for observation. So this is how they were able to see them. So the cloud containing the raspberry sugars mentioned were observed by a technique called rotational spectroscopy, and this was done using a 40-meter Yeeves radio telescope and a 30-meter IRAM telescope, both located in Spain. So even floating alone in the freezing vacuum of space, the molecule is never really completely still. It does rotate. But because of the laws of quantum mechanics, it can't just spin at any random speed. It is restricted to a very specific and discrete rate. As the molecule shifts between the energy levels, it emits or absorbs radio waves and at incredibly precise frequencies. So what happens is this creates a unique sequence of radio signals that acts exactly like a barcode for the molecule, or even a fingerprint, you could say. And it's unique to the specific arrangement of the atoms on the molecule. So by turning their telescopes to the exact frequencies predicted by quantum mechanics, the team could read these kind of barcodes and right through the cloud and picking out the unique signature of erythrulose from thousands of light years away. Pretty amazing, actually.
That's mind blowing. Yeah,
It is.
Yeah.
Oh.
So to capture these faint signals, the team conducted ultrasensitive broadband spectroscopic surveys, meaning that they spent hundreds of hours scanning a massive range of cosmic frequencies all at once. But it's not easy to find one specific sugar molecule in that mountain of data. So the raw data readout from the cloud contained tens of thousands of overlapping spectral lines, which means lots of molecules. And so, yeah, you had a mix of the molecules plus the sugar in at the same time. So to prove the sugar was actually there, astrobiologists actually relied on a flawless chemical blueprint of erythrulose previously measured in other high-precision physics laboratories. And through this, astronomers were able to analyze their telescope data and match 12 distinct spectral lines confirming the presence of the gas phase erythrulose in the interstellar cloud. So they found the raspberry sugar. So it's not just the discovery of this molecule in space that's been surprising, but its abundance. So for decades, the gold standard theory in astrochemistry was that it's like a bottom-up model. So the idea was that molecules in space are built up slowly, kind of like Lego stacks, Lego blocks stacking one by one. So you start with a single carbon atom and you add a second to make a 2-carbon chain, and then you add a third. And if this step-by-step rule was the only way things grew, then a simple 3-carbon atom sugars like glycerol aldehyde and dihydroxyacetone should be common because that's what they are. While larger 4-carbon sugars like erythrulose should be quite rare. But when the team analyzed the data, they discovered something strange. Erythrulose was at least 8 times more abundant than the 3-carbon sugars. In fact, despite using incredibly sensitive equipment, the team could not even detect the simple 3-carbon sugars at all. So this discovery shows that space kind of likes to skip steps in molecular assembly. By collaborating with quantum and astrochemical modeling, the researchers of the study were able to show that instead of building atom by atom, smaller pre-made 2-carbon pieces, specifically a simple aldehyde called glycoaldehyde and an alcohol called ethylene glycol, can simply snap together. They completely skip the 3-carbon phase to create large complex sugars and instantly in a massive quantities. So space really isn't a slow basic builder. It's a highly efficient chemist. Pretty cool. Now, as a side note, the research team calculated that the historical impact of this space sugar meant that based on massive amounts that they detected in the molecular cloud, they estimated that between 500,000 and 50 million tons of erythrulose could have rained down on the young Earth, when Earth was developing. So delivered by heavy bombardment of comets and meteorites over 4 billion years ago, this cosmic sugar would have dissolved directly into our planet's primitive oceans. Once in the water, the molecule could easily shift and rearrange its structure into other sugars, providing an instant ready-made building block for the very first metabolic and genetic processes.
Amazing.
So it could have been that, they do talk about life not actually starting on Earth itself, but starting from the molecules that came from space onto Earth. And this is another project that, kind of leads scientists to thinking that way as well. So there you go, raspberries in space. That's not really what I said, but yes.
I'm disappointed that we missed the sugar rain by a couple of million years. I would have liked to experience that in person. That would have been all right. A bit of
How
sugar
good
rain.
would sugar rain be?
Be great.
I have to make a shout out to all the diabetes. Just take it easy, guys. It's good. Take it as,
Speak for your people, Lino.
Nice,
that's good.
nice.
Yeah,
It's all good.
right.
Sugar's not bad. We just can't take a lot of it, but it's a good stuff. Oh, sugar from space.
Mm-hmm.
Caroline, I'm totally serious. That is just mind blowing knowing that. Wow. But you can't. When a time we have time travel, we have to totally divert away from those clouds. Yeah, Caroline, we can't fly.
Oh, you don't want to
ships.
go in there. No, don't go
I was
there.
about to say, definitely.
I will chance this for humanity, everyone. I will be happy to
Yep.
The good thing is we have like beautiful sugar come from sugarcane and other fruits and vegetables on our beautiful earth. So just pack it in a bag and take it with you. That's probably
I know.
Serious question that I don't know your better answer. So is the sugars in raspberries the natural sugars, right? So it's the same sugar. So is this the space sugar, or is it just now like, you know, it, like you said, it rained on the earth as you talked about, and then, you know, became part of, you know, Earth's molecular structure, I know I'm putting this pretty badly. And now it's just here continuing, you know, through raspberries. You know, like, why raspberries? Why not like anything else? Like, what's the deal?
Well, it just so happens that it is the same kind of sugar found in raspberries. It's not really that there's a connection to raspberries.
That's what I was wondering. Like, is there a connection to this ancient space sugar and raspberries today? Yeah.
It's more like those molecules landed on Earth, the beautiful natural processes that happened with the basic, you know, blocks, the molecular blocks that needed to create life did that, and life couldn't help itself forming. And then over time, let's be specific about raspberry plants. Raspberry plants developed over millions and billions of years, and then they were able to then create their own erythrulose, you know.
Okay. A unique blend that it made itself. Yeah.
Exactly. Right. So for some reason that plant makes that kind of sugar. But yes, no, it's not that they're integrated into raspberries.
Right.
But,
okay, that's what I wanted to know.
That's what you meant.
Yes, that's my layman question. Yeah. I would have been disappointed if you know, if a galaxy called the Milky Way didn't have any space sugar in it. So I'm actually
love that.
This is the way it should be.
It just makes sense, right? It just makes sense.
Now I get why they call it the Milky Way. That's
What? Mm-hmm. That is wow. I
also now want a Milky Way, but that's a whole other problem. Yeah.
Thanks.
I also want a sticky date pudding, but that's also another problem.
You also made me think
double yum.
That's what I'm thinking about now.
Is that a hint? Is that a hint?
It's a hint. You need to make one. As soon as you thought sugar, I thought sticky date pudding. It's the first thing that came to mind. Yeah. But this time I want it with raspberries.
Raspberry date pudding, sticky raspberry pudding. No,
I don't know.
That might work.
It might work. Yeah.
Might invent the first raspberry mess.
Plenty of mess in the kitchen.
All right. That's a fascinating topic. I love that one.
Let's Science is brought to you by StarQuest Media and is a fortnightly podcast that brings you the scientific wonders of our universe from a distinctly Catholic point of view. For more from Caroline, Lindsay, and friends, listen to the StarQuest show, Catholics of Oz. Find links from today's show at sqpn.com/science and find the Catholics of Oz at sqpn.com/Oz. Be sure to follow the show in Apple Podcasts, Google Play, wherever you can find podcasts, or on the SQPN YouTube channel. The generous donations of our patrons at sqpn.com/give make it possible for us to continue Let's Science and all the shows at StarQuest, which makes our nonprofit mission possible. You can join them by visiting sqpn.com/give. Join us next time for more scientific wonders, and thank you for listening to Let's Science on StarQuest. Here's another show on the StarQuest network you're sure to enjoy, The Secrets of Stargate. Find it wherever fine podcasts are found or at sqpn.com/Stargate.